Here are some helpful instructions for the lab called GeoWorld. This will be helpful if you didn't have time during class to finish the entire exercise. I always encourage students to make sure to read the introductory material instead of just jumping right into the questions. Find out what the lab is going to be about. In this lab, there are these pre-lab questions, and they're pretty basic. Number 1 asks you what a divergent plate boundary is and to give an example. Number 3 asks about convergent plate boundaries, and it asks you to define and give an example of each of the subtypes. So you're going to kind of have to squish that in there. There's not a lot of space to write. And number 4 asks about transform boundaries. Now I skipped number 2 because number 2 is kind of a different question, and it's a good one to think about. How do divergent plate boundaries come into existence? Number 5 in the pre-lab section is how can the rate of plate movements be determined? So rate is simply speed, and speed, as we've talked about in class, can be determined by taking the distance that something travels over the amount of time it took to do that traveling. So that's pretty much the answer for number 5. We then move on to part 1, which is called seafloor magnetic anomaly analysis. Again, I encourage you to read the first sections and make sure you understand where we're heading. Now this first paragraph describes this magnetic polarity timescale on the right. I've shaded some text here that indicates that the shading in this timescale indicates normal polarity of the magnetic field, meaning the magnetic field points to the present day north. On the other hand, the white bars in this timescale on the right indicate reverse polarity. So anytime you see along this timescale a shaded box, it means that the polarity is normal. If it's white, it's reversed. And of course it flips back and forth as we have learned. And I won't do any more, but there you get the idea. Remember that at the very top is 0, meaning 0 years ago. This is the present time. This is 50 million years into the past, 100, and 150. In class, we have looked at the Earth's reversal timescale, and it looked like this. It was colored to indicate different ages of seafloor and called the digital isochrons of the seafloor. So remember, isochrons are regions on a map that show areas of identical age, and usually that's on the seafloor. So for example, everything in the darkest red is between 0, which is present day, and 9.7 million years of age. And you can see that mostly this is occurring along the active spreading center, so that makes sense. Anything that's blue in this map is between 154.3 and 180 million years of age. So in this case, we had color indicating the age of the seafloor. In the lab today, we only have this alternating set of gray and white isochrons. We can take this colored one and put it on its side to kind of match up the timescales to show you how similar they are. So we have the present here, we go back into the past as we go down, and again, the only difference is that we have a gray and white shading pattern versus colors that indicate not just reversals, but give us a little more information about the age. So we could have looked at isochrons in class with a black and white map, and it might have looked something like this. So even though the colors are nice to have, they're not absolutely necessary to understand seafloor spreading. Speaking of seafloor spreading, here's an animation that shows you how the magnetic polarity of the Earth's field is recorded in rocks at spreading center systems when brand new ocean crust is forming. Here we have time. This is showing 200 million years ago, and this is showing whether the polarity is towards the north or the south, and red is indicating the directions. So in the beginning frame here, the magnetic polarity is to the north, and I'm going to hit play. We start with the land spreading apart, a new sea forming, and now we have ocean crust forming, and it's recording with the arrows the direction of the magnetic field. So I'm going to pause now and show you what we have. We have a symmetric set of isochrons, right? The middle part here is where new seafloor is forming. And as we go further away from the center, we get older and older seafloor, right? The oldest isochrons are where the continent initially broke up and started forming brand new seafloor. Remember that When the arrow is pointing north, when the magnetic polarity is to the north, we are recording directions to the north, and that's indicated with these arrows pointing north and also with the color of the crust, just to kind of emphasize that it's normal polarity. We're only at 53 million years now, but let's keep going. Okay, and now we have the entire series. So remember, this is how those isochrons form on the seafloor. Hopefully this helps you solidify in your mind what we're actually looking at when we're looking at isochrons. Okay, so here we are back at page 3 of the lab, and we have our magnetic polarity timescale. Now let's look at the map that goes along with it. Now this map might be a little confusing at first. I'm going to give you a larger view here. It's maybe a little bit tricky to see, but what we are looking at is down on this world called GeoWorld, where there are continents and oceans and islands. On the right here in the east, we have a continent called Frodo Continent. In the middle, we have another continent called Bilbo Continent. And between them, we have an ocean called the Elrond Sea. And what you can see on the seafloor are the isochrons that were formed during seafloor spreading. We have another set of isochrons and an ocean over here called the Aragorn Ocean. We also happen to have something called a trench, and then we have some islands. So if it's hard for you to see where the land and where the water is, I made a little color overlay that might help you. So here I've colored the land green, including the islands, and anything that's water blue, all the oceans. I'm not going to use these colors for the rest of the discussion, but if this is useful, maybe you want to take a screenshot and keep it handy. Okay, so we're back with just the black and white version. The first question here, number 6, asks which of these two oceans is showing symmetric isochron patterns and which is showing an asymmetric isochron pattern. So you just saw the animation where seafloor spreading tends to make a symmetric pattern. Let's look at the patterns in the two oceans. Is there any place in this set of isochrons where you could essentially put a mirror and divide in half the pattern? And I think there is. I think if you put a mirror right here, you would see that you had a skinny reversal in white in both directions, and then a skinny normal chron in the gray shading in both directions, then a wider white on either side, then another slightly skinny, normal polarity, etc. And if you keep going back and forth, it does seem to be symmetrical. On the other hand, if we look at any one of these seafloor segments here, let's just take a look at this one. We have a large white in the middle, but to the left or the west, we have two rather long normal crons, and to the east or to the right, we have some short ones. They don't seem to really be symmetrical, and then another long period of time for normal. So there really isn't anything symmetrical in the pattern in the Aragorn Ocean. So the answer here is that the Elrond Sea has the symmetrical pattern, and therefore it has active seafloor spreading. Question 8 asks you to highlight the mid-ocean ridge and the one that's active, and we've already kind of talked about it. It's the one in Elrond Sea, and to label it Hobbit Ridge. So I've gone ahead and done this with a pink marker. If you have a red one, that works well for divergent plate boundaries, and I've labeled it Hobbit Ridge. At the bottom of page 3, it asks you to make a 1 to 2 sentence explanation of the origin of these striped patterns, which I've just kind of gone over. Question number 9 asks you about the pattern of the negative and positive anomalies and how you could figure out how many millions of years ago this seafloor began spreading. So one thing that would be helpful to understand when this started is to figure out the age of this oldest chron on the outsides. Remember in the animation that when seafloor spreading began, the oldest material wound up being at the edge as the ocean got larger and larger. So one easy way to do this maybe is to give labels to these normal crons, and I've just done it with the alphabet, and maybe this way we can see some patterns. So I've labeled them A to L, A being the youngest, and if A is the youngest, then this chron in the middle must be A because we've decided it's active seafloor spreading. Then we have B on either side. And again, we're just labeling the normal crons. C, D, E, and finally F. So it looks like this ocean began opening during the time of normal cron F. If we look at the timeline here, notice that we have 10 million year increments. F occurs somewhere around the 60 million year mark. Let's say 60. You could maybe say 61 or 62. That's up to you. Question 10 asks you to figure out the rate of spreading. They call it half spreading rate, and I'll explain that in a moment, for Hobbit Ridge. How fast has the Frodo continent, for example, been moving away from the ridge? So first of all, you're going to need to know this distance. There's a scale bar down here, and you can use this to measure against the scale bar. Or you can use this information here, which is that 1 centimeter on the map is about 400 kilometers on GeoWorld. Unfortunately, the map sometimes gets photocopied into a very small size, so I wouldn't actually use this information necessarily. In any case, you can use this little scale bar down here pretty easily. For this example, I am going to use 1,000 kilometer distance, even though I know it's longer, because I want you to figure out how long this distance actually is. I'm going to show you the math using 1,000 kilometers, but really it's going to be more than 1,000, right? As we said before, distance over time gives us a rate. So our distance is 1,000 kilometers. Again, not really. Over 60 million years, which is how long it's been spreading. And so you just divide that and you get 17 kilometers per million years. Now there's this really interesting conversion factor that probably only geologists use, which is that if you have a number described in kilometers per million year, it's the same as saying millimeters per year, because they're both a factor of 10 to the 6. There's 10 to the 6 years in a million years, and there's 10 to the 6 millimeters in a kilometer. So if we have 17 kilometers per million year, that's the same as saying 17 millimeters per year. And that's the answer you would put there. But again, 1,000 isn't correct. It's going to be a little bit more than 1,000, so do it more accurately. The next question asks you, what is the full spreading rate? So this was the half spreading rate. What if we want to know the speed at which Frodo and Bilbo continents are moving away from each other? Well, you're simply going to double this number. Now they want you to use the magnetic anomaly pattern in the other ocean to determine when the seafloor spreading started to form. So now this is a little trickier because here we have a pattern that's somewhere in here, but we don't have the present day. We don't have a starting point. So if you take a little time and look at the pattern here, especially these two normal crons that are close together, and remember the older parts are going to be at the edge of the continent. So we have these two that are small, short crons, and at a little bit younger age we have two more that seem to be together, but they're a little bit longer in time. And that probably indicates this time period right here. So this large normal period is probably K, and everything probably started between K and L. And then we go as far as the reverse cron between F and G. And so you can use that information to try to figure out the rate of seafloor spreading here as well. You have distance and you have time. Once again, you can find the rate. Okay, part 2. It says to highlight another plate boundary. So we've highlighted the ridge. There's also a trench, a convergent zone, which we typically color blue. So go ahead and do that. I also want to emphasize that there are actually transform boundaries on this image as well, because whenever we have offset spreading centers, those are offset by transform boundaries. Okay, question 15 asks you to give an example of each of the following on GeoWorld: a divergent plate boundary, a convergent plate boundary, and a transform boundary. So I think you can do that because I've just gone through that pretty carefully. Question 16 asks how many lithospheric plates are there in all? Next comes the geologic cross-section, and this is rather tricky because we haven't done this before, so I'm definitely going to help you with this. So down here between A and A prime, we are going to do a side view that goes right through the map area here, as if we could slice through the earth and look at it sideways. The first thing I want you to do is draw a straight horizontal line somewhere about halfway between the bottom of this cross section and the top and label it sea level. And we're going to start by transferring all of the information along this line that tells us we are at sea level. For example, here where the Frodo continent meets the ocean is 0 in terms of elevation. It's 0. And so down here we know we're going to have a point where we're going to have land to the east and submerged land to the west. Similarly, right here we have a coastline. You can think of these as coastlines, as well as here. And then this island also is going to pop up. So I suggest you put a little dot where these arrows intersect the sea level. I wouldn't draw these arrows real dark, or maybe I would even just use a ruler. Use your imagination a little bit and make the land above sea level. Okay, so here I have this land here, and I have it rising from sea level. Then I have this section here, which includes the Rivendell Mountains on the left, and I kind of drew them like that. And then I have this volcano island here that I've drawn like that. Next, we want to put some underwater features. Let's start with the ridge. We know the Hobbit Ridge is here. It's going to be underwater. So I've kind of jumped up to the top of the screen here because I'm going to show you a series of drawings. And we know that that ridge is a little bit elevated compared to the seafloor around it, but then eventually it connects to the two continents. I use the red arrows to emphasize that this is a diverging plate boundary. Then I drew the underside of the lithosphere here, right? We can't just have nothing going on below us. And then I eventually went further and indicated where the bases of the two continents were. Next, we want to finish the seafloor on the west side, and we have the trench. So we know that the trench is where two plates are converging together, and when the teeth are on one side, we know that that is the plate on the top. So here I have drawn this section of the seafloor in the Aragorn Ocean going down and subducting below the Galadriel Islands. Next, you want to make sure you're clear on what is asthenosphere and what is lithosphere. And you can either do that by shading or using a pattern as I did here. So the instructions say show the entire thickness of the lithosphere and part of the asthenosphere, which I have done. It then says to label the crust, mantle, lithosphere, and asthenosphere. So I haven't done the crust and mantle in this particular video because I got to leave something for you to try, right? So think about where you would put a boundary for the crust and the mantle on those diagrams. Finally, the last part asks about the origin of the volcanic islands. And I'm not so concerned about the rock type because we haven't talked about that, at least in this class this semester. However, those three sets of islands, Galadriel, Gandalf, and Gollum Islands, are all in different tectonic settings. And the one hint I want to give you is this. Notice that the Gandalf Islands only have one at the very end of the chain of islands that seems to be active. That's what this little spurting cloud of ash is. And not only is it the only one that's active, but it looks like as you go further from it, the islands are smaller and smaller. In contrast, the Galadriel Islands are a long chain and all of them seem to be active. The third island, which is a little bit covered up here, Gollum Island, is by itself. It seems to be on the Hobbit Ridge and it is active. I hope this was helpful and that you enjoyed visiting GeoWorld.